In this video, we are going to introduce tangent spaces and our mathematically precise notion of a vector field. So in multivariable calculus, you learned that a vector field was a choice of vector in Rn at every point. So a choice of some vector in, say, R2 or R3 for every point in R2 or R3. So what you did, so say for example on R2, you would maybe draw your axes, and then at every point you would draw a vector maybe to visualize what was going on, although you couldn't obviously draw them all because there's one at every single point and you can't draw all of them. So this isn't quite right, because what's happening here is really there are two, whoops, that does not look right, two R2 or R3s going on. So the first is the manifold. The manifold R2 or R3. So in the manifold, we think of the manifold Rn. This is a bit of an aside. We think of Rn as being made up of points x1 through xn, and we're going to use these round brackets. And then so round brackets to denote points in Rn. And the second R2 or R3 is the one where the vector lives. So there's all these points at the bases of all these vectors, and they've kind of, they're vectors, but they're not based at the origin. And so these, I should have actually drawn these in a different color. These correspond to what point in your manifold, your vectors are based at. And then the second R2 or R3 is sort of at every point a vector space R2 or R3. And that sort of lives at every point, and a vector field is a choice of vector in that vector space. Your book has some really great pictures in section 2.2 of this phenomenon and how it helps you to sort of think about separating these two concepts of Euclidean space. So I suggest looking at that. So section 2.2. And the way that we're going to not confuse these two things notationally is when we think of the manifold Rn as being made up of points with round brackets, we write vectors in the vector space Rn with square brackets, so x1 all the way through xn, and they'll be column vectors. Okay, so what is this vector space doing, sort of living at every point and containing vectors in a vector field? So what we need to define is the tangent space. To every point x in a manifold M, there is an n-dimensional vector space called the tangent space to M at x, and denoted T sub xm. And it's defined in one of several ways. Well, so we're going to define it in one specific way, but here are several ways you can think of it before we give the precise definition. So first of all, it's sort of the closest linear approximation to M at x. So what does that mean? That means, say if M, so I love my sphere. So say if M is this sphere, and I want to take the closest linear approximation. So say x is this point here. I want to take the plane, right, because m is two-dimensional, so t sub xm should be two-dimensional at every point. I should take the plane that is kind of the extension of whatever this plane is at this point. So, you know, it extends farther than this. I'm just sort of drawing a piece of the plane. And it's going to contain vectors, right? And there's maybe, you know, maybe using my coordinates from the previous video, I have some way of thinking of there being like an x-axis in here and a y-axis, but we'll get to that. Don't worry about the axes yet. So the second way I have of thinking about the tangent space is if I take, so I have some coordinate chart and I just take the composition. So I have a coordinate chart u phi, and then I should just take d phi inverse of the Rn, which is the space yn plus 1 equals all the way out to yk equals 0, intersect with V, remember from my definition of manifold in the previous video. So I just take d phi inverse of this linear subspace, and it will give me some linear subspace in Rk. That will be sitting, you know, in some relationship to M, and you can prove that these are actually sort of the same idea. My third method is maybe the one that is most familiar. This is the space consisting of all vectors based at x and tangent to curves in Rk passing through x and contained in M. So with my handy dandy sphere again, essentially I'm thinking of this, I'm taking, you know, a bunch of curves. Maybe I have a curve that goes like that. Maybe I have another one that goes like that. They all have to pass through my point x, and you know, maybe one goes like that. But if I take their actual sort of infinitesimal directions that they're going as they pass through x, they're going to span some plane in Rk. And the faster I parameterize them, maybe the longer the vectors will get, and so I'll end up with an actual plane. So none of these definitions are actually right. There's a couple of different ways to define the tangent space, but we're going to pick one which I think is the most understandable at this point. So, right, so the problem is that we're sort of visualizing in all of these definitions, we're kind of visualizing the tangent space as living in the same Rk as M does. And that can kind of work to an extent, but it actually is a completely different abstract vector space. And, you know, it gets complicated, right? When you think of really long vectors and you think maybe if M is really curvy, its tangent space could intersect itself, and we don't want that to happen. So the way we're going to define the tangent space is an abstract vector space consisting of, so whose vectors are equivalence classes of curves in M, so curves in Rk that are contained in M, passing through X. So the curves, I'm going to call them gamma. Curves in X passing through, so instead of writing this all out, I'll just say they're passing through X at 0. So with the property gamma of 0 is equal to X. Where we consider gamma and gamma prime to be equivalent if the derivative of gamma at t equals 0 is equal to the derivative of gamma prime at t equals 0. So this is just the regular sort of vector valued derivative. So gamma is, you know, it's some set of k set of k functions, and with input from R, you can just take the derivatives of all those functions. They all have to be equal at t equals 0. So this kind of makes sense. It's very similar to our third definition, although, right, so this is now an abstract vector space. It's not actually something in RK. So what would happen here is, for example, if I had some vector, so these are all curves that would not be equivalent under this equivalence relation, but maybe I have some other curve that lives in M that does that, right? So these two, I'll color over the curve that I mean. This black and this purple, I would still consider equivalent because they're sort of pointing. I mean, maybe it's not super clear. They're sort of pointing in the same direction when they pass through the yellow point X. And that's how I'm going to define the tangent space to a manifold at a point. And on your homework, you're going to show that this is actually a vector space. And so we say gamma is, so if gamma is a smooth curve, et cetera, passing through X at 0, we say that gamma is tangent to a vector v in txm. I'll put a little subscript x to let me know that that v is in t sub x. At x, if, you know, d dt of gamma at t equals 0 is equivalent, so is in the equivalence class v sub x. And if I can generalize the idea of tangency. So gamma, I can say that gamma is tangent to a vector, even if maybe gamma doesn't pass through X at 0, I can just reparameterize it so that it does, and still think of gamma as being tangent or not tangent to a certain vector. So this is, so I've been stressing the difference between like the tangent space as sort of thinking of it as living in RK with M, and the tangent space as being this abstract thing. So it's really important to remember these differences when M is equal to R, is equal to Rn itself. So this is pretty complicated, right? Because so say if M is equal to S1, for example, you know, we're accustomed to maybe drawing the tangent spaces as like the space of all sort of lines that are tangent to M. But if M is R2, then the tangent space is, so here's my original R2, but then now at every point, I have like a tangent space living. And I can pick vectors, you know, of any length in any direction at every point. So we'll try to be really careful about this. So we're going to write vectors in the tangent space to a point x1 through xn in Rn as like this. So there'll be column vectors, and we're going to put the subscript x1 through xn on them so that you know. So for example, if I have like the point 1, 1, and I want to consider the vector 1, 0, what I mean by this, so this picture means the vector 1, 0 at the point 1, 1. So there's a couple of things we can do with the tangent space. The tangent bundle of M is the union of all Txm over X in M. So you take all the tangent spaces at every point and you put them all together. And a vector field on M is now essentially a function. Is a function, I consider it a function v from M. Oh, sorry, so the tangent bundle is denoted Tm, so no subscript. And a vector field is just a function from M to Tm where I require that v of p, or I think I'm using x here, v of x is an element of the tangent space to M at x. So we often confuse ourselves and draw vector fields on M itself. So for example, I think I drew some examples at the beginning. So yeah, we draw them sort of like this. Really, the tangent bundle to a manifold is twice the dimension of the manifold. So the tangent bundle to R2, for example, is R4. But that means it would be really hard to actually draw a real vector field in R4. So we make do by drawing some subset of the vectors in the vector field on our manifold itself. So I'll make note of a little bit of what I just said. The tangent bundle Tm is a 2n dimensional smooth manifold. So this is a claim that you might need to prove. Well, you do need to prove. We're not going to do it, but you can on your own time, or you can look up the proof if you're interested, or ask me. Right, so maybe an easier way to draw a vector field. So an example of a vector field. So we often draw vector fields on M as if sort of Tm kind of gets subsumed into M. But for one manifolds in R2, we sometimes one manifolds in R2, one or two manifolds in R3, sometimes we can do better. So if we are looking at, again, at the sphere, and I want to draw some vector field, maybe I'll draw the vectors when I draw them on the sphere as like pointing actually tangent to the sphere, instead of sort of when I'm drawing it in R2, I draw them as sort of lying on R2. And finally, some notation. Your book will write the vector. So the vector like e1 at the point x, x1. Let's just do the case of in R3, for example. This is just the vector like 1, 0, 0 at x, y, z, and sort of you can generalize this to higher dimensions and to greater i's for e sub I.